Endovascular interventions demand micro-precision. A fraction of a millimeter at the access site is often the deciding factor between success and a severe vascular complication. Achieving that precision requires navigating a disjointed toolkit. Unlike pharmacology or standard surgical instruments, endovascular tools do not share a unified measurement system. A single procedure requires the physician to translate continuously between an inverse gauge scale, standard imperial inches, and the anatomical French scale, calculating the math on the fly. The most dangerous assumption a practitioner can make in this environment is taking a numerical label at face value, believing that a stated size translates to a uniform physical footprint across different instruments. This side-by-side diagram illustrates the primary example of this discrepancy. On the left is a 6 French catheter creating a 2.0 millimeter profile. On the right is a 6 French sheath measuring 2.7 millimeters. Despite sharing the exact same 6 French designation, the sheath carries significantly more mass. Consequently, these two tools create drastically different arteriotomies, the literal puncture holes made in the patient's vessel. Understanding why this discrepancy exists is mandatory for mastering board-level exam questions and preventing unanticipated access site hemorrhages. Safe vascular access depends on tracking the shifting axioms of the coaxial system, following the math outward from the central microwire to the true physical footprint of the access sheath. We can derive these rules through a first principles approach, mirroring the actual clinical steps of gaining vascular access. We begin at the very center of the coaxial system. Looking at this cross-section of a puncture needle, the starting instrument, we see its size is designated strictly by its outer diameter. Needles are measured using the gauge system. Notice how the scale operates in reverse. The gauge system is counterintuitive. The smaller the number, the larger the physical needle. An 8-gauge needle is significantly larger than a 16-gauge needle. Once the needle punctures the vessel, the next layer of the system is introduced, the guide wire, which must advance through the needle's internal lumen. At this point, the standard changes. Wire diameters are universally measured in fractions of an inch. The standard reference point for general purposes is a 0.035-inch wire. Thinner wires, specifically 0.018 and 0.014 inches, are classified as microwires. You will also encounter glide wires. These are hydrophilic-coated variants designed to navigate small or tortuous vessels smoothly, but their diameters still adhere to the standard inch-based rule. While wire diameters are strictly imperial, wire lengths shift back to the metric system. They are typically given in centimeters, meaning a 180 wire is exactly 180 centimeters long. The foundational puncture tools operate on conflicting mathematical scales, inverse gauge against imperial inches. However, they share one crucial rule. Their stated size always refers to their external physical boundary. The next stage of vascular access involves removing the needle and tracking a catheter over the guide wire. At this layer, the measurement system immediately shifts away from gauge and inches, introducing the French scale for catheters and dilators. The fundamental conversion law of the French system is 3 French equals 1 millimeter. Translating requires simple division. 6 French equals 2 millimeters and 9 French equals 3 millimeters. The formula is the French size divided by 3 to find the diameter in millimeters. A critical piece of trivia to remember, the standard 0.035-inch wire will perfectly fit through a 4 French or larger catheter. Observe the measurement brackets on this catheter cross-section. The stated French size describes the external diameter of the tool, not the caliber of its internal lumen. Up to this point in the procedure, the structural logic holds steady. Whether measured in gauge, inches, or French, the stated size has always dictated the exact outer footprint the tool leaves in the patient's tissue. The logic breaks at the final outermost layer of the system, the vascular sheath, which is tracked over the catheter. Clinically, a sheath acts as a permanent gateway, allowing the physician to exchange multiple catheters and wires throughout a case without losing vascular access. Mechanically, this means the sheath must be able to securely house a catheter entirely inside of it. This reveals the central paradox. Because a sheath is a container, it is the only tool designated by its inner lumen size. A 6 French sheath simply possesses an internal void exactly large enough to house a 6 French catheter. If a sheath's stated size only describes its empty internal space, the physical material of the sheath itself represents unaccounted mass. It is a hidden variable that will stretch the patient's artery. This brings us to the specific board exam requirement of reverse engineering a sheath's true size to calculate the exact millimeter measurement of the skin hole. To find the true outer diameter of a sheath, you must account for the physical thickness of the sheath's rubber wall. Looking at this cross-section of the wall material, we apply a universal constant. The outer wall of a vascular sheath adds 2 French, or 0.6 millimeters, to its profile. To find the total outer diameter, add this 2 French wall thickness to the inner French size. Failing to add this 2 French constant before dividing by 3 results in an undercalculated arteriotomy. On paper, it leads to incorrect board answers. In the suite, it leads to unanticipated clinical bleeding. Let's apply this to a common scenario, calculating the exact puncture hole in millimeters created by a standard 6 French sheath. In our first calculation, 6 French refers to the inner diameter. Adding the 2 French wall thickness gives a total outer diameter of 8 French. Dividing that 8 French total by 3 to convert to millimeters, we find it creates a 2.7 millimeter puncture hole. We can now evaluate a more advanced, layered scenario, calculating the arteriotomy of a 6 French sheath placed coaxially into a short access sheath. This nested cross-section illustrates the logic trap. The short access sheath is the outermost layer touching the tissue. It must accommodate the 6 French sheath, plus its wall, meaning the short access sheath has an 8 French inner diameter. Adding the 2 French outer wall thickness results in a 10 French total outer diameter. Dividing by 3 reveals a 3.3 millimeter arteriotomy. Mastering the coaxial system requires tracking the shifting definitions of size, from outer gauge to inner French capacity, to accurately engineer the access site and ensure patient safety.